this is not about caching, this is about main memory, but I just want to cover it briefly also because it's related to compression also. Going forward, I think mechanisms that reduce the waste in structures like main memory and caches will become a lot more important. And there are some issues in compressing main memory that's targeted in this work. Again, this is another of the readings that I've assigned. The summary, I'm going to go through this relatively fast. But in general, I think we don't want large structures. We want to efficiently utilize those small structures as much as possible. And that's true of memory also, because memory is a cache for something else, right? That's the disk. So main memory is a limited shared resource. And this will become even more clear when I talk about main memory specifically in the next set of lectures. It's becoming more limited. Capacity is limited because we're adding more cores, but we don't have that much memory. I'll show you some results later in the next set of lectures that show that the memory capacity per core is reducing by 30% every year. And we're having more applications. If we continue that trend, we're not going to get better performance as we go into the future. So this is a limited shared resource, and we would like to utilize it more efficiently. The observation is that there's significant data redundancy. We've already made that observation. So the idea is to compress data in main memory. The problem, again, is the latency increase. Whenever you compress data in main memory, you get a latency increase. And that's because of multiple things. And I'll show you that multiple things. One is the decompression latency. And decompression latency will hopefully be solved. This is less of a problem in main memory, because main memory latencies are already very high. But the second is the address computation latency. That's also interesting. Whenever you need to access a location in main memory, and if your compression algorithm is not amenable to nice address calculation, you can get a very long address computation latency. So the solution I'll propose is, again, this is work by my students Gennady, is linearly compressed pages. Basically, the idea is keep the granularity of compression at fixed sizes. Don't have variable size compression, because if you have variable length compression, it's going to be very hard to figure out the address of a location. And that's the simple idea. I think I can stop here maybe for this work. But I'll give you just a little bit more. So it turns out if you do this, you can get a compression mechanism that increases capacity, 69% on average, that decreases bandwidth consumption in main memory by 46% and improves overall performance by 10%. And we actually evaluated this with GPU applications also. And their decrease in bandwidth consumption is about 50% and increase in overall performance about 50%, because GPUs are bandwidth limited, and anything you do to reduce that bandwidth directly impacts performance. Okay, so there are several challenges in main memory compression that this work targets, and I'll focus on this one. One is address computation, mapping and fragmentation, and the third is physically tagged caches. These are going to be easy to handle, so I'm not going to cover this in detail. There's, of course, always the complexity in all of these. And there's one complexity is actually the compression complexity. So what is the address computation issue? If you look at an uncompressed page, you know exactly where a cache line starts. Right? If you say cache line 5, you can easily compute its address, because there's a linear mapping between the cache line's number and the address. You take the base and linearly add the size of the cache line to figure out the location of the cache block. When you have a compressed page, you do not know where a cache line starts if you do not have a nice format. And that's the problem in many previous works. If you have a compressed page like this, it takes a long time to figure out what the address is, because there's a serial dependence. Right? You have to figure out what's the address of this to figure out the address of this. You have to figure out what's the address of this to figure out the address of the next one. So that's the same problem whenever you have variable length encoding. So we're going to try to get rid of this problem. The second issue, which I'm not going to discuss in detail, is mapping and fragmentation. This can be solved relatively easily. If you don't have a compressed memory, you have these virtual pages that look like this. And they map to physical pages that also look like this. But if you have compressed memory, your physical pages look like this. Right? Some of them are small, some of them are big. So you do not know the physical page size, but you can encode it. This is easily solvable. But you also get fragmentation. Then the question is, how do you actually put these different pages in different locations? So you can actually segment the memory to different, you can divide the memory into different physical size blocks and then allocate from those blocks. But this problem can be solved, and people have looked at this. So physical caches pose another problem. Whenever the core generates a virtual address, this is on the critical path, you do address translation, you get a physical address, and you have L2 cache lines over here. And this physical address could be different from the main memory address, right? Because now you have now your cache lines are actually at different locations in main memory. So you need to do the right translation. But I'm not going to cover this also again. So shortcomings of prior work. I'm going to focus on this part, the first part, which is address computation. People have actually implemented compression mechanisms. IBM has processors or memory controllers. It's called the memory extension technology. That is described in detail in IBM's papers. That is a relatively complicated mechanism. It has variable length compression. It does something similar to LZW compression, which is expensive. As a result, it has high access latency, high decompression latency, but great compression ratio. And IBM can afford it because they can design these very expensive systems and sell it to those few people who can afford to buy those. But if you're not IBM, you cannot do that probably. And even IBM has simpler mechanisms today. So the solution they had to the address computation problem was to add a huge cache. IBM had a 32 megabyte cache in 2000 or so in its memory controller, such that they could bring these cache blocks that are compressed into that cache and compress them, store them in compressed format, and then decompress them afterwards. And I'm not going to go into that detail again. Their potential, that way they didn't need to compute the address as much. They could overlap the latency of the address computation with that access of the cache. There are other mechanisms, robust main memory compression. This employs frequent pattern compression, and it has better decompression latency because it does use better compression, simpler compression algorithms. It has good compression ratio still, not as good as LZW, but its complexity and access latency are high because it still does variable length compression. So we're going to try to achieve, again, all of these together. We're not going to be able to achieve as good compression ratio as IBM MXT because LZW compression is by definition variable length compression, but that's a very high bar to shoot for. Okay, what's the key idea? So this is what an uncompressed page looks like. And to compute the address of a cache line, again, there's a linear mapping. We're going to try to preserve that linear mapping. So this is how our compressed page will look like. And compressed page will support only some compression ratios. In this case, we're going to support, this is a page that supports a 4:1 compression ratio. So we're going to have slots in the page that keep compressed data, 1 kilobyte. So each cache block can be compressed to 16 bytes. That could be as little as possible. And we're going to have some metadata. If a cache block cannot be, this metadata will say, for each of the potential cache blocks, is this block compressible with this algorithm, with this ratio? And if it is true, then we have a bit that's set to 1. If it's false, then we have a bit that's set to 0. If the bit is 0, then we cannot store the cache block in 16 bytes over here. So we have some exception storage, saying that these are the cache blocks that cannot be stored within 16 bytes, so they're going to be stored in full size here. That's the idea. So this is the storage for compressed cache blocks. This is the metadata that says, is a block compressed or not compressed? And this is the storage for those blocks that are not compressed. And this is the page structure. Now we have a bunch of these page structures for different compression ratios.
So for one chart that's compressed, then how do you find the address of those?
Yes. So this metadata also stores pointers to those. So this metadata is bigger than just 1 bit.
Okay.
Yeah. But that's a good question. And if in the end a page is not compressible, if in the end the size of the page doesn't fit the size of the page that's allocated, we're not going to compress that page. Again, we have a bunch of compressors that will determine, can we compress this page with 4:1 compression ratio, or 8:1 compression ratio, or 16:1 compression ratio, or 2:1 compression ratio. So that's the idea, basically. I don't think I need to give a lot more detail, but there are a bunch of issues with it that we solve. Basically, we need to have extensions to page table, compression type and size. There needs to be an extended physical base address. There needs to be support in the operating system. We have 4 memory pools for different pages, page sizes. There needs to be changes to the cache tagging logic to solve the problem that I described, which I'll not go into. You need to handle page overflows. For example, you can write to a page, and now the page becomes uncompressible. So you need to handle that case, right? And the memory controller will handle that. And you can actually use different compression algorithms. And we're going to use BDI and FPC. Again, BDI is simple. FPC is more complex. So some optimizations. One important optimization is to have a metadata cache. Because whenever you access a cache, a memory for a cache block, you don't want to access the metadata first, because that requires 2 memory requests, right? If you need to access the metadata to figure out whether the block is here or here, that requires 2 memory accesses. Whether the block is in the compressed part or actually in the exception storage, that requires 2 accesses. We don't want that. So we're going to have a metadata cache in the memory controller. And you can get away with a small one. This also leads to memory bandwidth reduction. For example, if you have actually 4 contiguous cache lines, you can transfer them with 1 transfer instead of 4 transfers. So we're going to take advantage of that. Instead of, whenever we request a single cache line, instead of transferring a single cache line that's compressed, we're going to transfer 4 cache lines, or n cache lines that are compressed, if they are contiguously compressed. And that gives us memory bandwidth reduction because we're more efficiently utilizing the memory bandwidth. With 1 transfer, we're getting a prefetching effect. And we handle 0 pages and 0 cache lines. This is not that interesting because people have proposed this before. And it's easy to do, right? If you have a fully 0 page, it's easy to compress it. And these exist, by the way. Fully 0 pages exist because of initialization. More than I would think, and more than perhaps you would think, unless you've dealt with them before. But also there's 0 cache line compression that figures out which cache lines are 0. And we've integrated with this cache compression. And the best benefits are achieved if you do both cache compression and memory compression at the same time. And I'll show you some results. These are actually old results. The results in the paper that I've mentioned are more up to date. So we have several event-driven simulators to actually evaluate this. One is Symix-based, one is multi-2-sim based for the GPU results. Again, we're using heterogeneity in experimental methodology also, because different experimental methodologies are better for different kinds of systems. And there are a bunch of workloads. I don't think I have results with the GPGP applications here, but I don't have many results anyway. So this is the compression ratio comparison. This is the geometric mean across a bunch of workloads, and this is the compression ratio you get. So 0 pages, you get 1.3 compression ratio, which is surprisingly high. If you do frequent pattern compression, you get 1.59. If you do linearly compressed pages with base delta immediate, you get 1.62. You can actually employ different kinds of compression algorithms because different pages may be compressed with different algorithms. So if you do that, we can increase the compression ratio to 1.69. So we use here base delta immediate and frequent pattern compression, a different version of frequent pattern compression that makes it work better. This is IBM's MXT, which is much higher, 2.31, but its complexity is much higher also. And this is the LZ compression, Lempel-Zil compression, which is a little bit higher than IBM's MXT. So IBM's MXT makes some simplifications, like it reduces the size of blocks that can look at. And LZ is applied in the entire memory without regard to any size. That's why it gets better compression ratio. So this is probably the best you can achieve in memory compression, at least within reasonable bounds. I'm sorry? Oh, that's hard to figure out. Yeah, IBM has some numbers. I think it takes 50 cycles or much longer to compress a page, decompress a page in IBM's MXT. And this will probably be much higher. The compression time of base delta immediate compression is much faster. You can do it in 5 cycles if you hit in the metadata cache. So it's much faster decompression latency over here with LCP. So we're not considering these parts because these are very complex. For the other compression ratios, we get competitive ratios with other mechanisms. The bandwidth consumption decrease, this shows the decrease in bandwidth consumption when you do memory compression. And this is normalized bus accesses per kilo instruction. And again, averaged over all workloads, and lower is better. And 1 is the baseline system. FPC cache is if you employ cache compression only. BDI cache is if you employ cache compression only. and you do base delta immediate, and you do frequent pattern compression. So bandwidth is reduced if you use cache compression. If you do memory compression with previous mechanisms, bandwidth is reduced much more significantly because now you're transferring less data over the bus. Right? The reason for bandwidth reduction in cache compression is because you're accessing memory less. Right? That's the reason. Whereas here, you're bringing less data from memory. That's why you're getting reduction. Now, this is LCP with a base delta immediate compression. This is just memory compression and no cache compression. We get similar compression ratio to the baseline memory compression mechanism. This is what happens as you employ both cache and memory compression together. This is previous work, and this is our mechanism with linearly compressed pages and base delta immediate. And this is also a combination of a bunch of different approaches. So the bandwidth reduction is significant. That's the key conclusion here. So this is just a comparison of performance improvement. I'll not dwell on this again, but you can improve performance significantly because of both the bandwidth reduction as well as better cache utilization. This is what happens if you use just memory compression. This is what happens if you use memory compression and cache compression together. And this is what happens with the mechanism that has different kinds of compression mechanisms. There's additional complexity here if you employ multiple different compression mechanisms. Here, the latency of compression actually matters a little bit. Here, the latency is lower. Here, the latency is higher. That's why it's better to pick this one, perhaps. But these are preliminary results, so take this with a grain of salt. Okay. So I promised that this would be quick, and this was quick, hopefully. Basically, this is a new main memory compression framework. The key idea is you have a fixed size for compressed cache lines within a page and a fixed compression algorithm per page. And you have a linear mapping between the address, the number of the cache line and the address of the cache line. And these are the performance results. Actually, I guess I did omit the energy results, but this actually decreases energy consumption on the bus significantly.